Okay, this is lecture 14 on specific force and rapidly varied flow. We're going to talk about and derive the specific force equation, and we're also going to discuss rapidly varied flow, which is actually section 5.5 in your book, which starts on page 152. We're not going to go into great detail on rapidly varied flow. I just simply don't have time in this course. I spend most of my time from here on out for the open channel section of the course talking about gradually varied flow, but I think we need to spend a little bit of time on it. You need to have some knowledge of it, and you will have a laboratory exercise where you'll look at a hydraulic jump and do some computations on it. So this lecture is necessary to understand the idea of the hydraulic jump, specific force, and the various things that you're going to need to understand to be able to do the laboratory exercise, and also have a sort of a conversational ability or some familiarity with what we term rapidly varied flow in case you encounter it in your future professional life. Carrying over from our equation that we had in lecture 13 for the momentum in the x direction, you'll see on the left side we have the forces in the x direction. On the control volume, you have the pressure force on the upstream side, and you have the pressure force on the downstream side. You have the weight force in the x direction. You have the friction force on the boundary. And then on the right hand side of this equation, we have the momentum flux across the upstream control surface of the control volume, so that would be the upstream side, and this would be the momentum flux through the downstream surface of the control volume. If we assume that this is a short horizontal reach, so we have no change in the elevation of the bed, we can essentially say that the slope is going to be S sub O is 0, so we're going to have no gravity force in the x direction. Also, if it's very short, we're going to say that the friction force is equal to 0, so you can see up here I've canceled these two out. That makes this momentum equation this form with a simplification where we just got the pressure forces counteracted by the change in the momentum flux on the upstream and downstream side control surfaces. You'll note that if we substitute in Q over A, which is the continuity equation for V, and divide through by the unit weight of the fluid, which is gamma, if we rearrange, we get this form of the equation. Now, I want to make mention again that this YC1 and YC2 are not depths, but they are distances from the water surface down to the centroid of the flow at the area, the flow depth there. So again, we're going to be looking at, in this cross-section view, YC1, YC2 would be this distance from the water surface down to the centroid. Now, we're going to, this equation here is just a carryover from the previous slide, but we're going to define something we're going to call specific force as Q squared over the acceleration of gravity times the cross-section area plus the cross-sectional area times the distance to the centroid, YC, which would be the specific force at section 1 would be on this side, specific force at section 2 would be on this side. And if we go through here and we have at a particular cross-section, we can, at various depths all the way through, we can define a specific force for each one of those depths. And what you see here is Y versus specific force. So much like we do on the specific energy diagram, we can have a specific force diagram. Now, if I look at that value for specific force being F is equal to Q squared over GA plus A times the centroidal distance, YC, I can take the derivative of that specific force with respect to Y and set it equal to 0 and look what the terms are for that minimum value. Again, this is the same line of reasoning that I followed when I took the derivative of the specific energy, E, with respect to Y. I took that and I went through a number of derivations. I'm not going to go through these verbally. You can follow them along on the slides yourself and you can see kind of what I've done to manipulate things. But essentially, I'm taking differential calculus and I'm taking that specific energy equation and I'm taking the derivative of y. I use some various forms of integration, or not integration, but partial differential equations here. I'm having a memory lapse. Various techniques within calculus to look at busting this apart where I can solve for df dy. If I look at this and I say that df dy equals to 0, I'm talking about the minimum being right here at this location. Now, if I pursue this and set this and move on through, I can get that the differential with various parts of this equation. You can see the dq squared over ga on the next page, the dayc over dy. I break it down and show you that the dayc is simply equal to a dy. And then on the next page, I show that through working through the various tricks, I've got dq squared over ga with respect to dy is equal to this business right here. I can show that putting that together, I end up having minus v squared over g plus a over the top width, which ends up being the hydraulic depth, which you'd already described in a previous lecture. Further pursuing this a little bit, this becomes minus v squared over g plus d, which equals to 0. That's this minimum situation here. Going through and dividing both sides by d, I get v squared over gd, which equals 1. This should look familiar to you. It's simply the Froude number squared. And so what we're talking about here, when we have the minimum specific force, this df dy, we end up are saying that we have the same situation that we have when we have the minimum specific energy, where the Froude number is equal to 1. And so that's the critical condition. So at this location here, where this is minimum specific energy, that's also corresponding to the critical depth here. And note that's exactly what we had with specific energy. We had the same kind of situation where it was minimized. We had the critical flow depth. When you that location where you have a Froude number equal to 1, or the critical situation, not only do you have the minimum specific energy, you also have the minimum specific force. All right, so what are our conclusions on critical flow? So we had the lecture on specific energy on Monday of this week, and that was essentially that the specific energy is a minimum for a given Q. Specific force, now I've shown you that is a minimum for a given Q. And again, I want to remind you that this specific force diagram here is for a particular value of Q. And so as we go through, we have this Q that's constant, and we get this form, or this curve, that's based on various values of the depth. Now, getting back to the conclusions, we also know that the velocity head is equal to 1/2 the hydraulic depth. That's that whole business that I'd shown you on the board, where we went through and said the Froude number is equal to the velocity over the square root of g times the hydraulic depth. And then we went through a little derivation, and you can see that if I squared that out, v squared over 2g is equal to d over 2 for the critical condition. That's what we're talking about there. And then again, we've specified this many times, the Froude number is equal to unity. And then also that we've shown, and I'll show in a second here, that Q is a maximum for a given energy, and that the channel velocity is equal to the velocity of a small celerity wave. I was talking about this when I was talking about throwing a pebble into a quiescent pool of water, and the waves emanate out of from the center at basically the speed of square root of g times the depth. That's a small celerity wave speed. And so if you look at the Froude number equal to 1 for the critical flow condition, that means also that the velocity is equal to the square root of gy. So that's what that says in the second bullet. So let's look at this business of the maximum Q corresponding to a critical flow for a particular energy. So if I've got a specific energy equal to E1, I've got various specific energy curves that are based on what the different flow values are. So here is a flow rate of 50, here's a flow rate of 100, here's a flow rate of 300. And you can see that for a fixed specific energy, E1, that I get various values of y for each. I get two values for each curve of y that have the same specific energy. If I took a number of these curves, said I had, I've only shown you 3 here, but let's say that I had, 100 of these curves through there for, every a curve for every increment of 1 cubic feet per second. So I had one for 50, 51, 52, so on and so forth, all the way to 300. I could look and pick off the values of y versus q, and I would get this kind of a plot, which is the y versus q plot. And we would see that at the critical condition, when we get that 300 CFS, that's right here at this value, which is the demarcation between subcritical and supercritical flow. Furthermore, we can see that the y critical is equal to 2/3 the specific energy at that point. And that's just a throwback to where we say that if I've got their critical condition, I've got that the velocity head is equal to 1/2 the hydraulic depth. If I take that depth and look at that in terms of the specific energy, where I've got depth plus the velocity head, that essentially becomes 3/2 of the depth. Okay, that E is equal to 3/2 depth. If I turn that around and take the reciprocal, I basically am just saying that the critical depth, YC, is equal to 2/3 E. So there's nothing big there. That's just something that I've shown you already when I looked at specific energy when it's at a minimum. All right, so let's turn our attention to rapidly varied flow. And as I've said, the rapidly varied flow is covered in more detail in chapter section 5.5 of your book. That's at page 152. I'm just going to go through some various concepts. We will have some problems in the examples that we will work later on, but we're going to almost have to go through lecture 15, where you understand water surface profiles, for those problems to actually make sense. So I'd planned on showing these problems in the next class period, but I think I'm going to delay. Go ahead and work or give you lecture 15, and then have the problems the following lecture that have to do with rapidly varied flow, because they're not really going to make a lot of sense to you without the water surface profile lecture that I'll give, lecture 15. So if we look at rapidly varied flow, we know that it occurs when water depth changes abruptly over a very short distance. The curvature of flow is pronounced, and the pressure distributions cannot be assumed hydrostatic. Boundary friction is relatively small given the short distance. You get rapid changes of water area causing the coefficients of alpha and beta to be greater than 1. Remember that alpha is basically the kinetic energy coefficient that basically says that if we use the average velocity to represent the v square, the kinetic energy, we have to correct for that, because we know that the average is not a good representation when we're taking the square of the velocities all the way across. Same thing with the momentum, the Coriolis coefficient, the beta value, that's correcting for the momentum flux, and so those are going to be greater than 1. And so I want to show you really quickly what I mean when we're talking about rapidly varied flow. We're going to talk about a hydraulic jump. So let's show you that really quick. I'll shut up and we'll get around here. Let's see if I can pop this up. This is on the modules that we put together out in let's see here, out in Phoenix, Arizona, that I did for the Bureau of Land Management.
In this flume demonstration of the momentum principle, what we have created is a hydraulic jump. On the upstream side, we have a sluice gate, which is up beyond our measurement, up beyond our scale. And what we have then is we've created a hydraulic jump. We have very high velocity flow in the upstream section. Downstream, it's much slower and deeper. And what we're going to do is we're going to measure the upstream water surface and the upstream velocity, and then we're going to use the momentum principle to compute what the downstream depth is. And then we'll compare to what we actually have here in the flume. So let's take a closer look at what we have at the upstream scale. We see there that the depth is approximately 13 millimeters from the bottom of the flume, And you see the meniscus is varying quite a bit. The velocity fluctuates quite a bit when you have very thin flow like that. But it's averaging at about 77 millimeters. So with those two numbers, a depth of 13 millimeters and a velocity head of 77 millimeters, let's now go to...
Okay, I'm going to cut in at this point because you get the idea. I want you to watch. It'd be easier probably for you to click on that URL and be able to see this equation and about the hydraulic jump. This will also give you some idea of how the specific force equation is used. So this gives you an example, and I would like you to look at that on your own as part of this lecture. Okay, so moving along, we can see that the hydraulic jump, we have a supercritical flow on the upstream side, and we have subcritical flow on the downstream side. And this is basically the same specific force is on each end of this hydraulic jump, but we're using these conjugate or sequent depths, which we've seen that we had when we looked at the specific force diagram. You can see that for a particular value of specific force, we have two values of y that can satisfy that specific force. So those are conjugate or sequent depths. We had alternate depths, if you remember, in the specific energy diagram, where we had two depths that satisfied the same specific energy. If I look at the flume here, I can see that I've got hydraulic jumps here, and we can characterize, and you'll see this in the laboratory demonstration that will be done, or the laboratory exercise is done as part of the lab portion of this class. You'll be able to see these hydraulic jumps. But we have these various types of hydraulic jumps, from undulate to weak jump to a steady jump to a strong jump. These undulate jumps are kind of moving around a lot. The Froude numbers are not very high on the upper end, so they're not well defined. A very strong or steady jump, they have really high Froude numbers, and so the water's coming out from under the sluice gate here, supercritical, very high Froude numbers, and subsequently we have a very well-defined hydraulic jump. And these are not particularly good examples of strong jumps, but you kind of get the idea from these pictures here what we're talking about. This is a flow coming on in a trapezoidal storm channel here. You can see that as the flow is coming down, we're getting this kind of miniature hydraulic jump occurring right in here. And you'll get these in these very steep gradients. They're very difficult the hydraulics are very difficult here, and they're really difficult to model because you can have areas of supercritical, subcritical flow, supercritical. I'm getting ready to head to Colorado to work on the floods that occurred there in the Boulder area. And one of the things that we have a problem with identifying after the fact, trying to resurrect the flows from the water surface profiles, is that we can have sections which are supercritical, and then sections on a little bit farther downstream that are subcritical, and then it can go back when the slopes change back to a supercritical condition. And so you have going from super to sub back to super. It's very difficult to model the hydraulics of these large gradient streams. Here's another example of a hydraulic jump here in this particular channel. And then I wanted to show you, kind of contrasting the hydraulic jump with the specific energy curve and the specific force curve. If we look at our hydraulic jump here, we have the supercritical flow on the upstream side, and that corresponds to right here on the specific energy diagram. It would correspond to right here on the specific force diagram. Our hydraulic jump occurs, we lose a lot of internal energy, and so we've got some delta E that occurs here. This is horizontal, so we have no difference in the Z, the Z1 and Z2. And you can see that we're now in subcritical flow conditions, but we have lost specific energy, and we're back over to here. Now, characterizing that change of specific energy is what makes it problematic in these hydraulic jumps. It makes it problematic to model this with specific energy equations or energy concepts, because it's very difficult to predict this internal energy loss. Whereas for specific force, we do not, again, the specific force is all based on external losses or external forces, and so we're assuming in a very short distance here we're not losing much in terms of the friction force. We have the same specific force at the upstream end as we do at the downstream end. So that's why when we're looking at hydraulic jumps, we're going to use specific force in order to determine their locations. And so if you were designing a system below a concrete overflow spillway and you wanted to keep the hydraulic jump on the concrete blocks or on the concrete apron, you would have to use specific force concepts in order to model how much resistance that you had to have, or how many baffle blocks you'd have to have in order to keep that hydraulic jump on the concrete apron. And as we talked in class, you get the hydraulic jump off the concrete apron and you get tremendous amounts of scour because there's so much energy and turbulence in these hydraulic jumps. If I've got a rectangular channel, I'm going to quickly derive for you, and this is contained in section 5.5 in the rapidly varied flow part of your textbook on page 153. If I assume a fixed rectangular channel, I can represent the area A1 as B times Y1, and then A2 is B times Y2, and then the centroidal distance from the water surface down to the centroid is just Y1 over 2, and the same thing for the centroidal distance at section 2 is Y2 over 2. I can substitute those in. I get this particular form of the equation here. If I know that the flow squared is simply the area squared, so that's B squared times Y1 squared, times the velocity at section 1 squared, and I substitute that in and I can do some manipulation, I end up getting that Y2 over Y1 is equal to 1/2 minus 1 plus the square root under the radical of 1 plus 8, the Froude number at section 1 squared. And what that does is, if I can determine what the Froude number at the upstream end, where it's supercritical and above a hydraulic jump, if I know the depth, then from this equation I can predict what the depth is going to be downstream. Now, if I can turn this equation around, or I can get another form of this equation from the specific force, if I simply, instead of substituting Q squared equals B, Y1 squared, V1 squared, I substitute in Q squared is equal to B squared, Y, this would be, I'm sorry, yeah, the B doesn't change because it's uniform flow, or uniform channel. It's B squared times the depth downstream, Y2 squared, times V2 squared. If I substitute those into this equation here, I end up getting this form, which is Y1 over Y2 in terms of the Froude number at the downstream location squared. So those are these two equations are equations in your textbook. This would allow us very simply to say, if I know what the depth is and the Froude number at a particular location, either upstream or downstream, I can predict the depth at the other end of the hydraulic jump. There'll be some examples that we work. As I said, I need to go through lecture 15 before we show you some of those examples. There is an example in that lecture that we present on the thing that we did with the BLM out in Phoenix. So go back to that URL and see how that example's worked, and you'll understand how we use specific force to work with a hydraulic jump.